the district's going to be like, don't give your grade 11s rubber bands. I should be able to. This was wrecked by Brad. So, the definition of an elastic force is, it is a force that works to return a distorted object back to its rest state. That is the definition of elastic force. So you guys are, as you're playing with your rubber bands, this is the rest state of my rubber band. It doesn't want to be anything other than what it is. And if I apply a force to it, it's stretched a particular length. I can feel this thing pulling backwards on my thumbs, trying to go back to this. And so we take advantage of that thing. We say, okay, well, I'm just stretching the rubber band. And if I let go here of the left side, it's just going to restore itself. Those of you who can't see what I'm doing, I'm pointing it at Kai. If I let go of this left-hand side, all the rubber band is going to try and do is restore itself. And what that means is the back side is going to try and join the front side. Unfortunately for Kai, what that means is if the back side tries to reach the front side, it's going to go towards the front side. And then because this thing has mass and now it's moving, no, don't point it at his face from a foot away. It's a little different when I point it at you from over here. Right? If it hits you, it doesn't go quite so far. I'm allowed to shoot at you, you're allowed to shoot at me, but you're not allowed to shoot at each other. Okay? So we're bringing in all of these concepts. It's mass, it's inertia, it's elastic force coming back together. So there's examples of all of this kind of concept all over the place. You have a rubber band in your hands. Rubber bands, oh, that's a really terrible color to use, is one example. R-U-B-B-E-R-B-A-N-D-S. Rubber bands. Springs are another one. If you've ever had the misfortune of having to build a trampoline, you've played with springs before. They start all nice and compressed. You hook the one end, and now you've got to get the hook on the other end, to the frame. The first couple springs are easy. It's always the last 20 springs that suck. I have to go build one of these with my buddy next weekend, I think. It's going to be great. What other examples of elastic force can you come up with? Sire. Sorry? Bending metal. Metal wants to restore itself to it. So where do we use that concept in a practical, everyday kind of scenario? I'm picturing what you said. Yeah, works for me. But there's a more everyday example of such a thing. Do you have one, Raina? Oh. Oh. Not what Sire was going for, but mousetraps, absolutely. Mousetraps are wound tight by the cranking of the one arm, and then you lock it there. Mouse comes along, pushes the pad, releases the spring, slap. Mouse is dead, hopefully. You don't want the mouse to suffer, right? We don't want the mouse to be alive in the trap because that would be inhumane. What I was going for, Sire, when you were describing the act of bent metal wanting to straighten itself out and compress, that's one of the ways that shocks on cars are designed. They're bent. Some of them are actual springs, but some of them are just bent big bars that as they compress, they want to uncompress. And so you kind of get this bouncing effect as cars go down or trucks go down a rough road. So shocks on a car or on a vehicle of some. Some of them are springs. Some of them are actually just big bars of bent metal. You guys have examples of elastic stuff on you, in you, on you and in you. Your muscles have to be elastic. If your muscles aren't elastic, every time you went to work out and stretch them, you would just tear them and they'd be done. It's when you overstretch them is when they start to tear, and that's bad. But your muscles have to have a certain degree of elasticity. Yeah. Your skin also has to have a certain degree of elasticity. If you're not growing on the inside, or if you are growing on the inside, and your skin has zero elasticity, your frame just tears through your skin if your frame grows faster than your skin grows. Usually what happens is your body grows, and then your skin feels tight, and then it stretches to match your new frame. Whether you're working out at the gym, or you're pregnant, or you've eaten too much at dinner time, whichever one of these things happens to you, now you've got a portion of your body that's grown bigger than the skin was allotted for, and so now your skin has to stretch. So yeah, we've got muscles, we've got skin, and then most of sport is designed for this as well too. It's going on right now, so I'll show you a picture of this. Most activities in sport take advantage of the fact that the equipment that they're using has an elastic nature to it. So that's my daughter. Don't worry about that picture. This is the picture I want you to come here, you silly thing. This is the picture I want you to see. This picture here. NHL playoffs are going on right now. What's this guy doing? What is the act? Yeah, that is a slap shot. And slap shots are called slap shots because, I mean, for a few reasons. You wind your stick back as far as this thing, as far as the torso will twist, and then you just try and slap the puck. Now, in your proper technique, your stick is actually supposed to hit the ice first, and you drag with some force your stick along the surface of the ice. Doing that causes a bend in the stick here. For those of you who've never seen a hockey stick, this is not supposed to look like this. Hockey sticks are supposed to look straight. Now, all hockey sticks have as they're being constructed, a number associated with them that tells the user of the stick how hard it is to do this. The higher the number, the harder it is to bend the stick. So that if you are able to successfully bend the stick, the stick is going to want to reform rapidly. The higher that number, the more aggressively that stick is going to snap back into place. The more aggressively that stick snaps back into place, as soon as you get this stick blade off the ice, it's going to want to straighten. And if you can time it so that the straightening happens while it's in contact with that little rubber disc there. Oops, don't want to do that. Why did I click on the picture? Stupid thing. If you can cause the snapping of the stick to happen while it's in contact with that little rubber disc there, you're going to add massive power to your shot. And so that is the fact that these sticks flex and then want to come back is what makes a slap shot happen. The fact that bats have a certain degree of elasticity to them too, and that baseballs have a certain level of elasticity, is why home runs are a thing and why we watch sport. So many of these sports require this kind of property. So what Hooke discovered was, while he was examining these things, in his law states that the amount of elastic force is proportional to the amount of stretch. Is what he discovered for all things springy. Now, he didn't use the word stretch, he uses the word distortion, but I'll change it for the sake of making sense. Now, if I take a look at my rubber band, you guys look at your rubber bands, mine's there on the table. How much stretch does this rubber band have right now? 0. It's not distorted at all. And so it's when we take the rubber band, even if I do this, it still has no stretch. I've reoriented it, but I'm not stretching it at all. Now, if I put my finger here and I start to apply a force, it's starting to stretch. It's now been stretched a little bit further. This is what we would call, if I just hold it here, I'm not stretching it at all, I'm just kind of squeezing it together. This is what we call equilibrium. This is the base length of the thing without being stretched. Now, I'm going to make a mark on you don't have to do this, but I'm going to make a mark on my page right there. And that's going to be the base length of my elastic. He said the amount of elastic force is proportional to the amount of stretch. So if I stretch this thing to here, based on what I've just drawn, this is my base. Sorry, so you can see that extra dot. This is the stretch now. The distance between those two green dots. If I want to stretch this thing further, I could put another green dot over here. And everything is measured relative to this first green dot I drew. It was here at rest. Now I've applied some force, it's over here. I apply more force, now it's over here. So he says the amount of elastic force is proportional to the amount of stretch. The more you stretch something, the more an elastic wants to come back. And the way that looks mathematically is this. The force, we're going to call this force, which letter do I want to use? Let's call this force big E. Elastic force is, and now when a mathematician or a physicist uses this word proportional, what that is this symbol here. It's the fish symbol that you probably grew up drawing. The elastic force is proportional to this distance here, x, and that letter x in this case represents the stretch. And for something to be proportional, what that means is if things are directly proportional to each other, it means that for this to be proportional to this, it means that Fe, let's write it out now as an equation, not just a proportional expression. Fe is going to be equal to x, the stretch. And the way you change the proportional symbol to the equal symbol is you got to figure out what you have to multiply x by. In this case, we're going to multiply it by the letter k to get the equality. If things are proportional, it means they are equal if you can find the multiplier. If you can find the thing that multiplies the extension or the stretch and multiply them together, you're going to get the elastic force. And now again, x is the stretch. So if I could spell stretch properly, that would be good. Morning, Dwayne. This is the stretch from rest, whatever the rest state is. And now we're going to define this k value here. It's similar to friction. It looks like a similar expression of friction. Friction was force of friction equals mu Fn, where Fn was the normal force, and mu was a property of the two surfaces that were sliding past each other, which is the lab that you guys have been doing for the last 2 days. If you take a vinyl piece and you pull it over a desk, you take that same vinyl, you pull it over a strip of metal, you take that same vinyl, you pull it over a strip of plywood, you're going to get a different value for the coefficient of friction is the language we use around that mu. The same is true here. What kind of, are all springs built the same way? No. Trampoline springs, if you've never had the fortune of having to build one of those things, trampoline springs are real big. They're thick, they're tightly coiled, they're hard to stretch. What's an example of a spring that's really quite easy to stretch? So easy, in fact, that we make it a children's toy, a slinky. The properties are the same, they're identical. You have a slinky, you have a spring to build a trampoline. Functionally, they're identical. They're both coiled pieces of metal. But we don't hand kids trampoline springs and say, hey, kids, go play. Because this value here, this letter K, is different for these different springs. So this letter K here, we call the spring constant. And every spring has its own. Now the goal in manufacturing, if you decide you're going to start a trampoline company, you want all those springs to have exactly the same spring constant, and so you're going to build them all exactly the same way. But if you have your slinky and you've got your rubber band and now you've got your trampoline spring, all of those springs are different. They have different applications. If you put shocks in a car that had the same spring constant as a slinky, that would be a very uncomfortable ride. The shocks would fully compress. They would never bounce. Your car would slam against the ground as you're going. It would be awful. And so this value K represents how aggressively that spring wants to maintain its shape. The higher the number, the harder it is to stretch the spring. Yes? Those are the units. So if you take a look here, if I solve this thing for K, this expression, FE equals KX, if I solve this thing for K, I'm going to divide the X down. Forces are measured in newtons, and extensions are a distance, or stretches are a distance. All distances in physics are measured in meters. So if I solve this thing for K, I'd get a force divided by a distance. That's a newton divided by a meter. That's the units. This in brackets M here is those units for the stretch. So coefficient of friction had no units. Spring constant does. Spring constant is measured in newtons per meter. Good question. So we'll do a couple examples and then we'll start an activity. A student stretches an elastic band with a spring constant of 50 newtons per meter by 15 centimeters. How much force would they have to apply to do this? Well, here's what's happening. They have a rubber band. This is the rubber band at rest. This is the rest. And then they stretch the thing. Draw the picture with me. So you have to label these things. What it means to stretch the thing by 15 centimeters is that you've taken the rest length and you've pulled the thing out so that this distance here is 15 centimeters. It's not 15 centimeters long now, it's 15 centimeters longer than it was. So this is now the stretched version of this thing. So we want to figure out how much force they're applying. Well, everything in this unit starts with, well, let's do this. Let's make a free body diagram here. Starts with a free body diagram. You've got a student applying a force this way. There's your applied force out. And now the spring says, I'm really quite displeased. From this same point, I am going to try and restore myself. I want to go back to the way I was. And so that's what this elastic force is. It's the force of the elastic pulling back on the applier. Now, if you hold your rubber band here, what can you say about FA and FE? If you don't allow the thing to snap back, they're equal. There's no acceleration, the thing's equal. So at this state, we know that the force of the elastic pulling back and the force applied have to be equal. So now we can go ahead and say, okay, we can find FA knowing that FE is going to be equal to it. Well, let's go over here. The elastic force for every elastic starts here. We know that an elastic force is equal to the spring constant times the amount of stretch on the spring. We are told what the spring constant is. This right here is our value for K. That right there is the K value. So we are going to have a K of 50 newtons per meter. What's the extension? We're told in the problem that it extends 15 centimeters, but extensions shouldn't be measured in centimeters. They should be measured in meters. So how do I take centimeters and convert it to meters? How many centimeters are there in a meter? Divide it by 100. So that's going to move the decimal place twice to the left. So 15 centimeters is going to become 0.15 meters. So then this is the value that we're going to put in here for the stretch. 0.15. So that means that the elastic force is going to be equal to 50 times 0.15, which is 7.5 newtons. So now we can say, okay, well, how much force has the person applied to do this? If Fe equals Fa, and now we found that Fe equals 7.5 newtons, that means the person must also be applying 7.5 newtons. Comments, questions, concerns about what we've done. It's not overly difficult, it's just a new idea. Questions, comments, concerns, or if I'm moving on to the next example? Cool, let's move on. Okay, hockey player that no longer plays hockey. This guy's old, played hockey in the 90s, but he was feared in the 90s for having a devastating slap shot. Al MacInnis used to play for the St. Louis Blues, used a wooden hockey stick. Now this was the 90s was the era where hockey sticks were moving. If you've ever played hockey, you'll know this. Whereas when sticks were moving away from wood and towards a composite stick. He was one of the last guys still used a wood stick. Terrifying because a wood stick, it's like using a tree. Very hard to bend. If you are able to bend it, it's going to have a massive swing back. The guy was bombing slap shots at 102, 103 miles per hour. Just absolutely ridiculous. So, he used a wooden stick with a spring constant of 850 newtons per meter, and he was able to exert 525 newtons on the stick while taking a shot. So let's draw this thing. Here's the ice, and here's what this means. Here's your stick normally. It's a really bad version of a hockey stick. For those of you who play hockey, I apologize for what I've just done. Looks more like a golf club. So that's what the hockey stick looks like, not stretched. For a hockey player to stretch the stick, it's going to look like this. It's going to curve. That's really bad. That's okay. We've got our curve in here. So this is curved. This is stretched. What we're trying to find here is, what is this distance? The distance between the curve at its maximum point and the stretch. Well, while the thing's being held, we know that the applied force is equal to the elastic force. And the elastic force is equal to kx. The applied force, we're told, Al MacInnis was able to apply a 525 Newton force. And the stick has a spring constant of 850 newtons per meter. So 525 is going to equal 850x. So then x is just going to equal 525 over 850. Let's go over here. 525 divided by 850. 525 divided by 850 is 0.618. What are the units on that value? Meters. What that means is, what Al MacInnis was able to do let's pretend that this is his hockey stick. I'm not sure if I'm going to be able to do this. What he was able to do, if this is, maybe you can help me out. What he was able to do is, if this is his hockey stick being held here, Lachlan, I would like you to try. 0.618 meters is 61.8 centimeters. I'm going to try this. I've never actually done this before. Lachlan, I want you to grab the bottom of the stick and I want you to bend it to 62 centimeters. That's the flex he was able to put on his hockey stick, which is ridiculous. You can like walk. And his hockey stick was not, if you've ever seen a hockey stick, they're not thin like this. They're a lot thicker. Really quite impressive. I was afraid that piece of wood was going to break. I'm glad it did not. Okay. I've got a video to show you before this next example. It was in... okay, here we go. Okay. Okay. Here we go. This is one of my favorite videos to show in this course. Here we go. So, this video was taken during a game show that was popular at one point. I don't know if it still is, called The Amazing Race. Hands up if we've heard of The Amazing Race. Okay, cool. In The Amazing Race, people have to, you travel all over the world and you compete in various challenges. One of the challenges involved launching watermelons with a slingshot catapult at suits of armor, as you do. So here's the video. Oh. I don't know which one's Brooke and which one's Claire. I don't know. It doesn't matter. But whichever one of them's wearing the pink is gonna. Yeah, she's the one we gotta watch. Okay, here we go. Okay, here we go. So here's what she's doing. She is. That frame there is holding the elastic band. She puts the watermelon in the thing, and you pull back really hard. As soon as you let go, you've used a slingshot before, I hope. The thing, the springs want to restore, and so they apply all that force to restore the thing, and then when they're restored, the pumpkin, or the watermelon in this case, just keep going. Momentum. Beautiful thing. Or, sorry, inertia. Try to launch it. Okay. And okay. So you can see the stretch, yes? Okay. See how it restored itself? Okay, everyone watch, please. Henry, don't look away. When she let go, she didn't let go straight. She gave it a little bit of a twist. And so what happened was, the watermelon goes all the way back out, the thing flipped over, and launched right back at her. Like, I feel pretty bad for her. The best part is what her friend says here. Or sister. Might even be sisters. I don't actually know. Okay, listen to the sympathy of her friend here. Okay, here we go.
You have to finish. Oh, she has such a horrible. But that's the game, right? Amazing Race. You have to complete the challenge. She undoubtedly has a concussion. She absolutely is concussed. She took a watermelon. You know how big watermelon are. You saw it exploded. It hit her point blank in the face. It exploded. She's absolutely got a concussion. I feel quite badly for this girl. Her friend has no sympathy. Oh, her friend is brutal. Okay, so that's the question we're going to look at right now. Better yet, they actually make these slingshots that are big enough to launch people. It's a good time, wildly dangerous. Rather than a watermelon, we've got a 65-kilogram girl sitting in a redneck slingshot. That thing that was just built there, that is what's also known as a redneck slingshot. You just make the thing massive. That has a spring constant of 10.5 newtons per meter. If the thing is stretched 45 meters, so the redneck slingshot is built at the center line on the football field, and then is stretched to the end zone, what is going to be the initial acceleration of the girl when it's released? So here's the picture. You have your redneck slingshot. It is stretched. This is the center line on the football field. And she's over here in the end zone. Let's draw the free body diagram on her. We've got FG down. We've got FN up because she's sitting on the ground. And there's some applied force back this way. And there's an FE that way. That's the scenario we've got here. If you take away this applied force, holding her back, what's going to happen to the girl? She's going to get launched. So we want to figure out what her initial acceleration is at this point. So as soon as they ask you for the word acceleration, even if we're talking about springs, we're going back to F net equals ma. If you remove the applied force, the only force acting on her in the direction of motion is going to be the elastic force, restoring itself back to its posts. So we're going to have Fe equals ma. But we know the elastic force is equal to Kx. So Kx is going to equal ma. We can start plugging in all of these values. We know that K is 10.5 newtons per meter. We know that X is equal to 45. That is the stretch. Her mass is 65, and we want to find A. So now we can just go ahead and multiply these two together and divide by 65. You're going to find that her initial acceleration is 10.5 divided by 45, times 45 divided by 65. Her initial acceleration is 7.3 meters per second squared. What that means is, by the time she's here and the elastic band has fully restored itself, she's going to be moving how fast? Well, you don't have to write this part down. You can if you want, I suppose. VI equals 0. VF is what we're looking for. The acceleration is 7.3, and the distance traveled is 45 meters. So VF is going to equal the square root of 2AD. So 2 times 7.3 times 45 square rooted. She's moving at this point here. If the acceleration remains the same, her velocity there is 26 meters per second. She's moving at 100 kilometers per hour when she gets to these posts. She is moving as though she were a truck on the freeway or car on the freeway, obeying the speed limit. She's moving pretty good, is what this acceleration equates to. So welcome to Springs.
what I'd like you to do in the time that remains, we're going to come back and we're going to look at the spring activity tomorrow. It's not a full-blown lab, but it is a mini lab. We're going to do it tomorrow. Today, though, I want you to take, there's 4 questions here, and I want you to take a look at all 4. It's not overly complex, but it is something new for you to play with. I will shrink it. You know what? No, I want you to do it all. Not a lot of work. You can do it all. Those 4 questions there. With the time, you've got about 9 minutes left on the block. You could get most of this done, honestly. And I have given you some space. So that's what I want you to take a look at. We'll look at spring constant activity tomorrow on your Market Set Giver.